Hello, my name is Ted Ding, and I am a PhD student at the Edinburgh Center for Robotics. Today, I will present our paper estimating fog parameters from an image sequence using nonlinear optimization. My co-authors are Andrew Wallace and Wang. So given a sequence of stereo images when driving in fog, we want to reconstruct clear images and infer scene depth. That is our motivation. Just a brief introduction on the atmospheric scattering model, which is widely used when modeling the image formation through fog. So basically it says that the observed intensity I is a convex combination between the latent clear intensity J and the atmospheric light A. The coefficient is called transmission coefficient T, which is determined by the scattering coefficient beta and the distance between an object and the observer d. Now, so the major drawbacks of existing methods is that they rely on prior knowledge of the nature of the fog, particularly the atmospheric light A and the scattering coefficient beta. However, conditions can change rapidly, and this is not a viable strategy. In contrast, we developed a unified nonlinear optimization method to continuously estimate and update the fog parameters with a state-of-the-art performance, enabling us to reconstruct clear images and infer dense scene depth. So our strategy is to recast the fog parameter estimation problem to a constrained optimization, a nonlinear optimization problem. Our method consists of the following three stages: extract a local map, generate distance intensity pairs, and nonlinear optimization. So the first stage of our method is to extract the local map. We use a visual odometry or SLAM system to build a local 3D feature map from a sequence of stereo image frames. So the local map can be illustrated as a directed graph, indicating the observation relationships between the frame and the landmark. So on the right, we show an example local map containing 4 frames and 5 landmarks. We use a local map rather than a global one because of 2 reasons. Firstly, the optimization problem is confined to an appropriate scale. And secondly, it requires the fog to be only locally homogeneous, which is a more realistic assumption. The second stage of our method is to generate distance intensity pairs. So for each observation in the local map, we use d to denote the Euclidean distance between a landmark and a frame. And we use I to denote the intensity of a landmark's corresponding to the feature point in a frame. Both D and I are typically available from a sparse feature-based visual odometry or SLAM system. So the scatter plots are shown on the right. As you can see, there are 3 groups of distance intensity pairs, each corresponding to the observations of a particular landmark, and they are shown in different colors. So the third step of our method is nonlinear optimization. What we do is we build an optimization graph comprising edges and 2 types of vertices. And as you can see from the example graph on the right, the first type of vertex is a beta and A vertex, and because we assume local homogeneity of the fog, there can be only 1 such vertex in the whole graph. The second type of vertex is a J vertex, and there can be multiple of them in the graph, each corresponding to a particular landmark. An edge is connected between the J vertex and the beta and A vertex if there is an observation of that landmark. And we associate an intensity error epsilon with each of the edge. So the intensity error is defined as scalar difference between the observed intensity and the predicted intensity by the atmospheric scattering model. So we formulate an optimization problem. So our goal is to find the best set of parameters, beta A and J, which minimizes an objective function, which is essentially a weighted sum of the loss function of the intensity error. And as you can see, this is an constrained optimization problem with bound constraints. We have two optimization settings. The first is that we use a two-stage optimization strategy. The first stage, we choose the loss function to be the robust Huber loss to mitigate the effects of outliers. And in the second stage, we apply the square loss, but only evaluated on the inliers only. The second setting is that we appropriately set the lower and upper bounds of the variables, the weights, and the initialized values. So for evaluation, we use three data sets. They are all synthetic data sets. What we do is we add fog according to the atmospheric scattering model to simulate foggy images. For competitive methods, we consider three. The first one is least method. The second one is our modified version of least method. And as you will see in the results, we consider this modified version as a much stronger baseline than the original one. The third method we compare against is Berman's method, which estimates A only. So this table shows the quantitative results on KT color dataset. The first four rows shows the comparison between our method and the other three methods. And as you can see, our methods achieves the lowest estimation error and the lowest standard deviation. We also conduct additional experiments and ablation study, and the results are shown in the rest of the rows, and you can find more details in our paper. This slide shows the qualitative results and the two visibilities. So basically, we plot the beta and A estimates against frame, and the key observation is that our method generates the estimates that are closest to the ground truth values. In this slide, we showcase the use of our proposed method by connecting it to a simultaneous stereo reconstruction and defogging system. And in particular, we choose the one we proposed in one of our previous work. So as you can see, the depth images and the defogged images are shown generated by that system are shown on the right. So this demonstrates the use of our proposed fog estimation method for downstream tasks such as depth estimation and defogging. So to conclude, we have proposed an optimization-based joint fog estimation method, which only assumes the local homogeneity of the fog, outperforms existing methods in terms of estimation accuracy, and enables us to reconstruct clear images and infer dense thin depths. That's all for my presentation. Thank you. And if you have got any questions, please contact me through this email. Thank you.